Welcome to A-Level and AP Physics. In today's lesson, we will discuss one very nice question on KMT from October-November 2021, Paper 4, Variant 2. In this question, we will discuss what is meant by elastic Leen. We will also talk about assumptions of KMT, and then we will also discuss how to derive different formulae, especially how to derive average translational kinetic energy of molecules using ideal gas equation. So in this question, we will discuss some very important points about thermal physics. For part A, it is given to us one of the assumptions of kinetic theory of gases is that all collisions involving molecules of the gas are elastic. For part 1, we need to state what is meant by elastic collision. Let's try to understand the conditions for elastic collision. If you look at conditions, momentum of the system means the initial momentum has to be equal to final momentum of the system, and the total energy before collision has to be equal to total energy after collision. And the last condition, this is only for elastic collision, kinetic energy of the system before collision has to be equal to kinetic energy after collision. It simply means that there is no change in kinetic energy of the system, or simply we can say delta K is equal to 0. So this is the condition for elastic collision only. Collision is elastic if there is no change in kinetic energy. Means kinetic energy of the system before collision is equal to kinetic energy of the system after collision. So we can classify that kind of collision as elastic collision. If kinetic energy before and after is not equal, then we can say collision is inelastic. So we can say inelastic collision. If kinetic energy before is not equal to kinetic energy after, mean kinetic energy of the system has been changed, so we call collision is inelastic. But if you look at these first two conditions, they are true for inelastic and they are also true for elastic, and the main difference between elastic and inelastic is kinetic energy. If there is no change in kinetic energy of the system, we call elastic. If there is change in kinetic energy of the system, we call inelastic. Let's try to write down answer for this question. This question has only 1 mark, and simply we need to write down there is no change in kinetic energy of the system, or we can say no loss of kinetic energy of the system. So if you write down this 1 point, we will get 1 mark. Let me show you how you can write down your answer. This is how you need to write down your answer, but you have to pay attention to kinetic. If you simply say no loss of energy, you will get 0 marks. So you have to write down no loss of kinetic energy, because this is the main difference between elastic and inelastic collision. If you write down this mark, you will get 1 mark, and this is B mark. Means this has to be in your answer. For the second part, we need to state 2 other assumptions of the kinetic theory of gases. One assumption is given in part 1, mean collisions are elastic. So this is 1. We need to state 2 more. One assumption we can state is volume of molecules, means the total volume of all the molecules is much smaller than total volume of the gas, or simply we can say volume of container. Volume of the gas is always equal to volume of container. It simply means that if we have this container, let's say this is 1 container, and we have gas inside, and these are gas molecules inside this container. If we take all these molecules, and we place them in 1 corner like this. If we place them in 1 corner, so the total volume of these molecules is negligible as compared with volume of the container. Means you take all the molecules and you place them in 1 corner of the container, so the volume is negligible as compared with volume of the container. So this is what is meant by volume of the molecules is much smaller than volume of the gas or volume of container. And the second assumption of KMT is molecules are in random motion, or simply you can say gas molecules are moving randomly or in random motion. Random motion means that molecules have different speeds, mean the speeds are not the same, and their directions are also different, means they're moving in different directions. This is what is meant by random motion. So we can write down different directions. So these are two assumptions. If you write down, you will get 2 marks. This question has only 2 marks. If you have written 2 assumptions, you will get 2 marks. Now let me show you how you can write down a proper answer for this question. In this answer, I have mentioned 4 different points. So here is point 1, and this is the second one, third one, and fourth one. But you need to write down only 2 points. In our explanation, we have already discussed first point. We have also discussed the third point. If you look at the second point, in the second point, it is mentioned that no forces between molecules except during collision. It simply means that when the molecules are away from each other, there are no attractive forces between molecules, and molecules only exert forces on each other when they collide. So this is very important point. There are no forces between molecules. It also means that internal energy of the molecules is only equal to kinetic energy, is equal to kinetic energy of molecules. Because potential energy of the molecules is equal to 0, we are talking about ideal gases. Potential energy of gas molecules is equal to 0. Why this potential energy is equal to 0? Because there are no attractive forces between gas molecules. No attractive forces. And this is our assumption for ideal gases. In some papers, they will ask you about this one. This is very common type of question. So you also need to understand this one. Now the last one, collisions are instantaneous. Instantaneous means when molecules collide, the time of collision is very, very small. So we can say time of collision means when molecules collide with each other, that time is very, very small as compared with time between collisions. Time between collisions means when they don't collide. Time between collisions. Or simply we can say when molecules collide with each other, time of collision is negligible. It's very, very small. That's the reason we have written here collisions are instantaneous. But for this question, you have to mention only 2 points. You can write down any 2 assumptions. You will get 2 B marks. For part B, it is given to us a molecule of an ideal gas has mass m and is contained in a cubic box of side L. The molecule is moving with velocity u towards the face of the box that is shaded in figure 3.1. Here we have figure 3.1 and this face is shaded face. So we can write down this one is shaded face and molecule is moving towards this face. The molecule collides elastically with the shaded face and face opposite to it alternately. We need to deduce expressions in terms of m, u and l for the magnitude of the change in momentum of the molecule on colliding with a face. For this question, it is given to us the molecules collides elastically. It means the kinetic energy of the molecules before and after is the same, because in this case cube is not moving, so the total kinetic energy of the system remains same. It simply means that the speed of the molecule before and after collision is the same. Now we need to calculate the change in momentum. Change in momentum, simply we can write down delta P is equal to P final minus P initial. But we need to be very clear that momentum is a vector quantity. So vector has direction. In this case, we will take to the left as positive. If we take to the left as positive, it means momentum after collision is positive and momentum before collision, because this is to the right, so this one is negative, mean this direction to the right is negative. So simply in this case we will get this is mu plus mu, so the change in momentum is equal to 2mu, and this is our final answer. So simply we have to write down here 2mu. The main point here is momentum is a vector quantity, so we have to take one direction as positive, and this question has only 1 mark and this is answer mark. If you have written 2mu, you will get this mark. For the second part, we need to find the time between consecutive collisions of the molecules with the shaded phase. It simply means that molecule collide this phase and then move away from this one and then come back to this phase again and collide with this phase again. So we need to find the time between two consecutive collisions. Imagine that this one is the shaded phase and molecules hit this phase and then move away from this phase. So here is the second phase. This one is shaded phase. So let me write down. This one is shaded phase and this is the opposite phase. And the distance between these two phases, this is given to us and this is equal to L. Molecule will collide this one and then come back and collide with this phase again. So the total distance traveled, in this case we can write down, distance traveled by the molecule between two consecutive collisions is equal to 2L. And the speed of the molecule is also given, speed is equal to u. Now simply we need to find the time. So the time simply is equal to the distance traveled by molecules divided by the speed of molecule. This is elastically, and so when molecule collide with any phase, there is no change in speed of molecule. So simply we can say in this case time is equal to 2L divided by u, and this is our final answer, 2L divided by u. This is our answer. This question has 1 mark and that is answer mark. If you have written this answer, you will get this mark. For the next part, we need to calculate the average force exerted by the molecule on the shaded phase between two consecutive collisions. So in order to calculate average force, we need to find the change in momentum and we need to divide change in momentum by time. Simply we can say the average force exerted on the shaded phase between two consecutive collisions is equal to rate of change of momentum. Change in momentum we have already calculated, that was equal to 2mu, and the time between two consecutive collisions we have calculated, that is equal to 2L by u. 2L by u. Now from here we can simply cancel this 2 with this 2 and we can write down mu divided by L by u. So this is L by u. Simply we can say in this case mu multiply with u by L. So simply we can say this is equal to mu square by L, and this is our final answer, and this is the average force exerted on the shaded phase between two consecutive collisions. If you have written this one, you will get 1 mark, and this is also answer mark. For the next part, we need to calculate the pressure on the shaded phase if the force in third part is exerted over the whole area of the phase. Whole area of the phase. So in this case, this side is L and this side is also L. So the total area of the phase we can simply write down A is equal to L square. Question is asking us to calculate the value of P, means the pressure. So this is equal to force over area. We have to use the value of the force from the third part. We have calculated here force is equal to mu square divided by L. So this is the value of the force. We have to divide this one by L square, means by area. Simply we can say this is equal to mu square divided by L times L cube. L times L square means this is equal to L cube, and this is our final answer. This question has also 1 mark. If you have written this one, you will get this mark, and this is also answer mark. So simply our final answer for this one is mu square divided by L cube. For part C, it is given to us when the model described in B is extended to 3 dimensions and to a gas containing n molecules, each of mass m. Means the mass of each molecule is small m, and molecules are traveling with mean square speed. It can be shown that PV is equal to 1 over 3 nm mean square speed. P is the pressure exerted by the gas and V is the volume of the gas. Use this expression together with the equation of state of an ideal gas to show that average average translational kinetic energy of a molecule of an ideal gas is given by. Means with the help of this one, we can calculate average translational kinetic energy of molecule. T is the thermodynamic temperature of the gas and K is the Boltzmann constant. If we read this question carefully, hint is already given to us. We have to use equation of state for an ideal gas. If we look at ideal gas equation, simply we can write down ideal gas equation is PV is equal to nRT. N is the number of moles. We can convert this one into PV is equal to nKT. And this N is number of molecules. This capital N is number of molecules. We need to find expression for average kinetic energy of molecule, and Boltzmann constant is in our final expression. So it's better we can use this. So we can use this. If you're curious about this one, how we can go from the first one to the second, simply you need to understand is number of molecules and moles, how they are linked together. Mole is equal to number of molecules divided by Avogadro's number. So this is how you can replace N with number of molecules divided by Avogadro's number. This is equal to nRT. Now from here we can also write down PV is equal to N, and R means gas constant. If we divide this one by Avogadro's number, we can replace this one with Boltzmann constant. Means we can write down nKT. So it's also important, you need to understand how you can derive this one from PV is equal to nRT. Now simply we have to use this second expression and the given one. Let's say this one is third one. In this case you can see PV is equal to this, PV is equal to nKT. So we can write down 1/3 1/3 nm mean square speed. This is equal to nKT. In this case, N is on both sides, number of molecules we can cancel. So we left with 1/3 m times mean square speed. And this is equal to KT. Now if we multiply this side by 3, so we can cancel this one. So we have to multiply here. Now we left with mass of single molecule time mean square speed. We need to convert this one into kinetic energy. So we will divide this side by 2 and we will also divide this side by 2. This is average translational kinetic energy of each molecule. So simply we can say this is EK, and EK is equal to 3 by 2 KT. This is what we need to derive for part C. And this question has 2 marks. 1 mark you will get if you have written this expression. So this is C mark. And the second mark is the answer mark. If you have got the right answer, you will get 2 marks. For part D, it is given to us the mass of a hydrogen molecule is 3.34 times 10 to negative 7 kg. We need to use the expression for EK in part C to determine the root mean square speed of a molecule of hydrogen gas at 25 degrees Celsius. In part C, we have already derived average translational kinetic energy, and we have found that average translational kinetic energy is equal to 3 by 2 kg. And this temperature has to be in Kelvin because this is thermodynamic temperature. The unit for this one has to be Kelvin. Now we can simplify this. You can see this 2 we can cancel with this one. So we can write down mean square speed. This is equal to 3 times kT divided by mass of single molecule. We need to find out root mean square speed. So root mean square speed simply means that we have to take the root of this. If we take the root on both sides, we can find root mean square speed. Or simply we can say this is CRMS. Now we need to plug in values. So 3 is here. The Boltzmann constant, value of Boltzmann constant is 1.38 times 10 to negative 23. And temperature has to be in Kelvin. So it is 25 plus 273. So this is how we can convert from Celsius into Kelvin. We need to divide by mass of single molecule. Mass of single molecule is given here. 3.34 times 10 to negative 27 kg. Now we have to take the root of this. If we take root of this and do calculations in a right way, our final answer has to be 1.9 times 10 to 3 meters per second, up to 2 SL. So it's our final answer, up to 2 SL. This question has 2 marks. You will get 1 C mark if you have plug-in values. If you have plug in these values, you will get 1 C mark, C1 mark. And the second mark is answer mark. If you have got the right answer, you will get 2 marks. You can see from here, the speed of the molecules are quite fast. So molecules are moving very fast. Even temperature is only 25 degrees Celsius.